Hello, and welcome again to Thermal Live 2018. I'm Murray Slovic, Senior Technical Editor with Electronics Cooling here in Philadelphia. Thank you for participating in this year's two-day online event. We're about to wrap up day one of our event, but we still have some really great presentations lined up for you, so make sure to tune in again tomorrow. Today's last presentation, Fundamentals of Heat Transfer and Thermal Interface Gap Filler Materials, comes from Fuji Poly. It should run about 35 minutes, and a short 10-minute Q&A session will follow. We welcome audience participation, so please locate the Q&A panel on your screen and submit as many questions as you'd like during presentation. We'll answer as many as possible in the time allowed at the end. If you want a copy of this presentation, downloadable slides are available under the Resources tab at the bottom of your audience console. Our presenter today is Christian Miraglia, the Applications Engineering Manager for Fuji Poly. Christian is a graduate of the New Jersey Institute of Technology and has more than 10 years of experience working with thermal interface materials. So without further ado, please welcome Christian.
Thanks for the introduction. I would like to thank everyone for joining us on this webinar. My name is Christian Miraglia, and I'm the Applications Engineering Manager at Fuji Poly America. For those that may not have heard of us, we are best known for our thermal interface products, but especially our line of gap filler products. Fuji Poly is actually a secondary processor of silicone products. Basically what it means, we specialize in taking silicone rubber and giving it properties that you would not normally find in silicone. Things like electrical conductivity. We specialize also in giving it certain magnetic properties. We're also mostly known for our thermally conductive line. Our core strength is basically in the dispersion of fillers while still preserving the compliance you'd expect to have with a silicone-based material. A little bit about myself. I'm a graduate of the New Jersey Institute of Technology, and I've worked for Fuji Poly for over 10 years. And I've spent a good amount of that time working on thermal interface materials and applications. I currently work out of our Customer Engineering Center here in San Jose, where we provide application-specific testing for customers such as compression testing and thermal testing. This is our second Thermal Live webinar we've done. In previous Thermal Live webinars, we discussed things like compression characteristics of thermal gap fillers. It tends to be a topic that's overlooked, but for this webinar, we decided to really focus on the primary function of a thermal gap filler, and that's its ability to transfer heat from one surface to another. Other sales engineers at Fuji Poly and I have worked with lots of different companies globally and seen a lot of different thermal solutions for various applications. One of the things that they all have in common is that the selection process for a gap filler can sometimes get a little confusing, and that most thermal solutions are often left to the end of the design cycle. So the selection process is done kind of under a tight schedule. So hopefully this presentation will make the process a little simpler. So before we actually jump into the webinar, I like to go over kind of a quick discussion about what we're going to be covering. This webinar focuses on heat transfer in thermal gap fillers. So thermal gap fillers are a very particular type of thermal interface. A lot of stuff we're going to be discussing you can apply to things like phase change and grease materials as well, but I just want to kind of note that early on in the discussion that we are primarily focusing on gap filler type materials. So what we're going to be discussing initially is the concept of thermal heat transfer. So we're going to briefly discuss things like Fourier's law of heat conduction. We'll look at it and how it applies to something like a thermal gap filler. We're not going to be solving vectors or any kind of matrices or anything like that. We're going to be simplifying Fourier's law of conduction down, since the geometry of a thermal gap filler is quite simple. For many of you that have not had formal academic training in thermal heat transfer, the Fourier's law will be very familiar. One of the things we're going to be looking at is the analysis of an ideal thermal gap filler. So with a thermal gap filler, we want to find out what materials we need to select so we have an acceptable temperature gradient. We'll create a resistive network for a very simple common thermal solution. We will look at what information is available on the data sheets that help us select the appropriate material for our required thermal resistance. So we're going to do an analysis of a real thermal gap filler as well. As with many things we analyze, we specify there is an ideal and a real-world scenario. So we'll look at what to look out for basically. So things like pressure, the final gap size, the impact of the actual die versus the package actually plays a big part in there. So we'll look at that briefly. And then we'll finish up by looking at some tools and resources available for us when we're actually going through a design for a thermal solution. So before we go into the presentation, I would like to very briefly go over some of the terms and units we'll be using during this webinar. Very nice to see those up front so you don't have to sort of backtrack as we go through the presentation. The most common term you're going to hear here, and probably as you work in thermal interfaces in general, is the term thermal resistance. And basically, it's the reciprocal of conductivity, but in thermal interface jargon, it includes a very important resistance, and one that really requires us to use a TIM to begin with, and that's the contact resistance. So as you start to skim through data sheets, you want to keep this in mind, that basically the thermal resistance that you find on data sheets is not just the thermal resistance of the bulk material, but it also includes contact resistance between the hot and the cold side. So a very important key piece of information to remember. We do occasionally have customers that want to know what the discrete resistances are, the contact resistance and also the bulk resistance. Typically those aren't separated, those are just presented as one value. Other term is thermal gap filler. This has caused quite a bit of confusion. Gap fillers are a very particular type of thermal interface material. Gap fillers are used to fill in gaps between the cold and hot surface. Unlike greases or phase change that basically are only reducing contact resistance between two surfaces that are in intimate contact, the gap fillers actually acts as a thermal heat transfer medium between two separated surfaces. So, for example, you might have a cold plate that is a millimeter away from a voltage regulator, or a processor that might be 3 millimeters away from a large heatsink. So we're not talking about the microscopic gaps that cause contact resistance. When we talk about gaps, we're actually talking about intentional gaps that are designed in and actually have tolerances to them. And very important to remember, gap fillers should only be used in applications where that's strongly, something that's strongly understood. You know exactly what your gaps are and what those tolerances are going to be. As far as units go, some of those common units you're going to see obviously are things like watts per meter Kelvin. Very common, basically tells us the heat flow required through a given thickness and area and the resulting temperature gradient. It's important to remember that temperatures are always gradients and not absolute. So this applies to other units as well, such as thermal resistance, whether you see it in degrees C and squared per watt, or if you see it in degrees C per watt. Basically, remember that these are just temperature gradients per power. So the absolute temperature is really more of a function of the ambient. So very important thing to remember. Also, watts per meter Kelvin do not include contact resistance, as we mentioned previously, at least not when we talk about TIMs. Just like the ASTM 5470, for example, basically what we do is we take the delta of the thermal resistance and the change in thickness and we calculate conductivity. So what we're actually doing is we're backing out the impact of thermal resistance. So when you do see values like watts per meter Kelvin on a data sheet, keep in mind that that is not going to include contact resistance. Something that we'll also be talking about, obviously, is things like thermal resistance or thermal impedance. You'll see these in values of degree C and squared per watt on most data sheets. Some places you might see as a degree C per watt if it's a known, if the geometry is actually called out explicitly. Basically, reciprocal of the conductivity, as I mentioned earlier. The only difference is, again, when you see these things in data sheets, you're going to see them, they will include contact resistance. Watts, obviously, very common. You're going to see this quite a bit since we're talking about heat transfer. Basically, that's power dissipation, and that's basically in joules per second. So it is a rate. We just call it watts and go from there. Things like heat flux, also something you're going to see in the presentation. That's basically the amount of heat we're getting per specific area. Steady-state heat conduction through a mass can be expressed by using basically Fourier's law. Since thermal gap fillers are used for thermal conduction, not radiation or convection, it's appropriate to apply Fourier's law of conduction to them. Fourier's law is expressed by the equation you see here, where Q double prime is the heat flux in watts per meter squared, K is the thermal conductivity, and then we can see that we got a del operator, so we're working basically in a three-dimensional sort of vector field. And you see a negative in front of the K, which basically implies a negative temperature gradient as you move away from the source. Could also express it in the second equation you see here, where we actually look at it in more of a scalar type field, and then we can kind of figure out exactly which way the heat's moving depending on the temperature gradient. So Fourier's law of heat conduction is based on observation. So with Fourier's law, we do make some assumptions. One of the first one is we have steady state heat conduction. So we're not trying to find out the transient response of the material. In most thermal solutions, the transient response is not as important since most thermal solutions are designed for steady state. And when we're looking at thermal gap filler, it is even less of a concern since the mass is relatively small and steady state is reached fairly quickly. So I should say that it has actually very little impact on the transient response of the overall thermal solution. Something else you will see is there's a negative sign in front of the K, thermal conductivity. So this does not imply negative conductivity, of course, but what it tells us is that basically the temperature is going down as you move away from the heat flow. So obviously as you start producing heat, as you start to measure the temperature as you move away from there, the temperature is going to go down in the direction of the heat flow. Another assumption, we also assume that the heat source surface is an isothermal surface. We basically have the same temperature across the entire surface. Now, this is going to come up again later when we look at real-world scenarios, but for now we will look at more of an ideal application where it's even across basically the entire heat source surface. Another one is material is homogeneous. This is very important. So the K is constant throughout the material. In the case of a thermal interface material, especially a thermal gap filler, they're actually not homogeneous. They're actually made up of fillers of different sizes and different thermal conductivities. So these particles are basically suspended in a binder, which is basically, in our case, silicone. But because we're not worried about the temperature variation at the microscopic level, we can assume it's homogeneous, at least when it comes to analyzing a thermal gap filler in a thermal solution for an electronic assembly. Finally, we assume that the material is not reacting to heat or increasing in temperature either by latent heat or some chemical reaction that would cause an endo and exothermic reaction. Fuji Poly, our gap fillers are mostly silicone, so you're not going to have any type of reaction, at least between minus 40 to 200 C. So you shouldn't be seeing any type of endo exothermic reaction in any material that we would be offering. So with Fourier's law, we can pick any point and get a heat flux through that point, and the direction of heat flow is a vector for a given temperature field. We can take fairly complex shapes and temperature functions and know how many watts per meter squared and the direction of heat in which it's traveling. But we're not really concerned about the heat in all directions. And with Fourier's law, we can make some basic assumptions. We can say heat flows in the direction of the temperature gradient, which is common sense since 2 points that are at the same temperature will not have heat flow in between them. In the case of a TIM, we're not really working with a temperature field that has a gradient in all directions. In fact, the thermal gap filler pad, basically what we're doing is we're doing one-dimensional steady-state heat transfer. So essentially we're going to go ahead and eliminate some of these other factors, such as the heat flow in the X and Y direction. And we're basically going to focus on the heat flow that's going just through the gap filler itself. So for the sake of this discussion, we're just going to look at heat flow in the Z-axis. Since we're only concerned about heat flow in one axis of the gap, we only have to concern ourselves with the relationship between heat flux, the thermal conductivity of the material, and the temperature gradient in one direction. This means we're essentially solving a plane wall. We no longer have to concern ourselves with the vector, only the scalar value of the heat flow. We can also rearrange this equation so we only have to solve for heat for a given area, conductivity, and temperature gradient. Essentially, this is what we're going to use to solve our resistive network. And it's basically a rearrangement of a thermal conductivity. You basically see we've got heat, area, and a temperature gradient. So if we were able to rearrange this equation, we can actually turn this into watts per meter Kelvin. In the previous equations, we were solving for the heat flux in watts per meter squared and how it relates to the thermal conductivity and temperature gradient. But when we're working on finding the appropriate thermal gap filler, the variables are a little different. So we can rearrange the equation to find the variable. Basically, what we're looking for is a conductivity or resistance we need to satisfy a condition, which is basically a temperature gradient. In most thermal solutions for electronics assembly, the heat flux is fixed. For example, a bare die ASIC that will run at 10 watts and is 1 centimeter by 1 centimeter, or maybe a metallized PCB with a 5-watt LED. There's also an expectation for a specific temperature gradient. For example, a component cannot exceed 85 C while the ambient's 40 C. So essentially what we are looking for is the thermal conductivity required for a TIM based on the power density and the worst case temperature gradient between the heat sink heat spreader surface and the top of the component. Probably the most common way to start any type of thermal analysis is by basically creating a resistive network that represents the actual components that make up the thermal solution. A resistive network allows you to visualize the different heat paths to ambient and quantify them so you can calculate temperature gradients and eventually actual temperatures. We start by converting thermal conductivities to thermal resistances. Thermal resistances is basically the reciprocal of the conductivity, but note that I put an asterisk next to the thermal resistance. This is because this term is often interpreted differently. It is sometimes referred to as thermal resistivity if it includes the unit of area and thickness. In some cases, you'll just simply see it as K per watt or degree C per watt, or sometimes you'll see it include a surface area where you'll see K centimeter squared per watt. And this is how most TIM thermal resistance can be found on data sheets. So we'll look at this in more detail when we look at real and not ideal thermal gap filler analysis. So in order for us to build a resistive network, we're going to simplify the resistances to a temperature gradient per unit power, in K per watt or degree C per watt. And we do this by getting the product of the ratio of the gap filler pad, meters to meters squared, so basically the thickness ratio, or the ratio to thickness and surface area, and we multiply that times the thermal resistance. We basically do this for every component in the heat path to ambient. Most thermal interface materials will have that data in thermal resistances, so I suggest using these values and not the conductivity for your analysis like we did on the previous slide. The thermal resistances that you're going to see on data sheets for thermal interface materials, specifically gap fillers, are going to take into consideration contact resistance. So it's the best number to use in any type of analysis. In this analysis, our surface areas are fixed, and the thickness of the material will be another variable that we're going to look at actually as we go through material selection. So being able to pick different material thicknesses are going to help us from a mechanical standpoint. But for right now, we're just going to try to figure out what kind of thermal resistances we're going to need to satisfy our requirements. In a basic thermal solution for electronics assembly, the most common thermal resistances you will need to understand are the thermal resistances of the case of the component, thermal resistance of the thermal gap filler or other TIM you're using, and of course the thermal resistance of the heat sink that's getting your actual heat out to ambient. Now, important to remember, the heat sink thermal resistance is not as simple as determining the thermal resistance of the thermal interface or even finding the thermal resistance of the case, basically junction to case thermal resistances. So determining that is outside of the scope of the webinar. So in the case of our study, we're just going to basically use an arbitrary value. We're going to say we're going to use an aluminum thin heat sink that's basically the same surface area as our pad. We're going to call it 25 by 25 millimeter, and let's assume we've got a 30 millimeter height. Now that's not going to affect our analysis. The point I definitely want to make is when you actually start getting these types of values, you're definitely going to want to go to your heat sink supplier, and they should be able to provide this type of information for you. Once you have that, you'll be able to do a much more detailed analysis. So just a few points about a resistive network that are worth bringing up. Basically, a resistive network is a series of resistances, right? So each resistance is typically a component of the thermal solution. We can also have resistances in parallel if there's some other paths to heat flow. So if you want to be very detailed, you can actually apply resistances for heat flow through the PCB or through some other medium. But in the case of our analysis, we're just going to do a basic three resistance resistive network here. So again, the sum of all these resistances will give you an overall thermal resistance for the system, but you can also figure out temperature gradients for the specific component within the system. Okay. Typically, each component has a thermal resistance and should be a homogeneous K value. Of course, if you're not interested in the temperature gradient within the component, you could just treat it as one bulk resistance, and that will be fine for your analysis. Each resistance is joined by a node. So the nodes are basically where we're going to analyze for temperature gradients. And we say something has a certain temperature gradient, it's a gradient across a series of nodes. So we can analyze the temperature gradient for an individual component, or the temperature rise with respect to ambient for that component. So basically the nodes are all going to represent the interface for the components and the heat sink as well as the thermal interface material. So when we discussed Fourier's law, or when we left off with Fourier's law, we simplified the equation for heat transfer in one dimension only, and we rearranged it so we would solve for conductivity for a temperature gradient and a given heat flux. We can take it further and convert this to thermal resistances independent of surface area and thickness. As I mentioned previously, we have a given surface area already, so we don't need to concern ourselves with that. And also, not locking in a thickness in our analysis will allow us to pick varying thickness so we can have some flexibility on the mechanical side, specifically when it comes to stress created by the gap filler under compression. So keep in mind, these materials are going to be under compression. So ensuring that you have a lot of different thicknesses to choose from is really going to help out. If you lock yourself into one thickness, you might find that it's either too thick and it could create too much stress, or it's too thin and it's not going to make good contact. So when we do that, we can simply say that the heat flow is equal to the temperature gradient over the total resistance of the thermal solution. Or we can solve for a temperature gradient for a specific power and resistance. Now, the total resistance is not known since we still need to know the resistance of the gap filler. So let's take a look at a simple resistive network. So in this example, we're going to keep it quite simple, just for the sake of explanation. So we have a component that will run at 1 watt, but in some cases, let's say it's going to run as hot as 5 watts. It won't run at that power all the time, maybe only for certain customers in certain situations. Even then, it won't run for too long, but it'll run long enough where it's going to reach steady state, and we want to be prepared for that possibility. So we want to design a thermal solution for the worst case scenario. First thing we do is we want to understand the environment we'll be working in. Basically, that's the ambient temperature. In this example, we'll say that the system may be in an environment where the temperature ambient can be 40 C. This is not uncommon. It's probably fairly low. The ambience can run much hotter depending on your location. Let's say you're in Phoenix versus Anchorage. And the type of environment as well, if you're in automotive applications versus a data center or up on a telephone, obviously that would have a big impact on your ambient. Next thing we're going to look at is what our max temperature is for the junction. This varies on the type of component, but mostly due to life, sort of your life expectancy more than anything else. 150 C is usually the max temperature, but even running at lower temperatures will reduce the life expectancy of the component. In this example, the product is anticipated to be out in the field for a very long time. If there's any servicing in this example, let's just say that we won't be servicing this part of the unit. So in this case, we're going to be a little conservative, and we're going to say that we want to keep the junction temperature about 85 C. Now, if you need a lot of detail on what temperature you should be running the junction at, a lot of semiconductor manufacturers are going to give you that information very explicitly, and they'll actually give you a kind of an anticipated failure based on the junction temperature. So taking these two temperatures, we essentially need a thermal solution that will ensure that we've got a temperature gradient junction to ambient to be no more than 45 C. Next thing we do is we're going to build our resistive network. And in this example, the network, again, is going to be quite simple. We're going to only use 3 resistances to create a basic model of our thermal solution. We'll start with basic we see as RJC, and this is the resistance junction to case. A lot of times you could find these on a data sheet. Good thing to keep in mind is that it's very different from RJA or RCA. These are actually resistances to ambient. So in this case, they're actually convection. So we're not going to really concern ourselves with that. What we really need to know is what the resistance is from that junction to the top of the case. So in the case with the gap filler, again, because we're using conduction, we really want to focus just on the thermal resistance of the case, not so much how well it gets heat out to ambient. Of course, next is the thermal resistance of the gap filler. So we'll call this RTIM, and then finally we've got a thermal resistance for the heatsink, and we'll go ahead and call this RHS. So for the resistance value, we see we are working in units of degrees C per watt. Previously, at the previous slide, we saw how we got ahead and neglected the effect of thickness and surface area. So one of the things we're doing is we're assuming even heat flow through the component, through the TIM, and up to the heatsink with the same cross-section area. In this example, it's basically an inch squared. So in the previous slide, we started with Fourier's law of conduction and simplified it down to one-dimensional heat transfer. With this, we can calculate power density, conductivity, and temperature gradient. But again, what we want to know is what the thermal resistance is just for the gap filler itself. We need to know what resistance will give us the temperature gradient so that we get an overall temperature gradient for a given power. And considering we have 2 other resistances in series, we're going to go ahead and focus just on the TIM since we already know what the resistances are for junction to case and the heatsink. So in this example, we're going to go ahead and plug in the resistance of the heatsink and the junction to case, as well as the power and total temperature gradient. And we can calculate the missing resistance, which in our case is the thermal resistance of the gap filler pad. This is the maximum thermal resistance, so it's very important that we know that it's the max. So if we go with a lower resistance, we'll obviously get a lower temperature gradient. Obviously, we'd be performing better, but with higher performance comes a lot higher cost. So calculating a max resistance will also help you find a thermal gap filler that's cost-effective. We often see customers over-specify costly gap filler materials when a mid-grade or even a low-grade material will work. Again, there are scenarios where high-end material is required, but we see plenty of applications where a mid-grade or even a lower-grade material will satisfy the requirement. So once we actually go through the basic calculation, we find that the TIM, to satisfy the requirement of a 4-watt power density, or 4 watts through a 1 inch squared surface area with a max junction temperature 85 and max ambient at 40, we're essentially going to need a thermal resistance of 2.05 degrees C in squared per watt. So the next step is basically picking what material is going to work. So we generally will start with a catalog or some data sheet. So on the screen, you will see a screenshot of our thermal resistance table, and you can find this on our catalog or online, actually. So what you'll see is that you see lots of different thermal resistances for specific material grade. You'll also see them for the different thickness of materials that are available. So for example, something like our GR25A, that material comes in 0.5 millimeter, but also comes as thick as 4 millimeters. So you're going to see varying thermal resistances as you change thickness, but you'll also see a variance in thermal resistance as you compress the material more. So earlier on, we kind of left open the possibility of picking different thickness, and we'll see why in the next slide. It's really good to be able to have lots of varying thicknesses available. So the tables you see up on the screen basically went through a very simple exercise, and we circled all the resistances that are lower than what we have as a maximum thermal resistance based on our calculations. So basically what it is, all these materials that you see circled would be, under these conditions of course, would be good candidate materials. And what I mean by condition is compression. So as for the thickness, basically we can pick from a variety of different thicknesses within a material type. Again, this is going to be really helpful. So if we can fine-tune the gap, we can select a thicker material so we can ensure that we're not creating a lot of stress in components. Thicker pads tend to be more compliant than thinner ones. So having this as an option is really helpful. Once you start assembling these assemblies, what's going to happen is you'll start noticing stress as you start to put together things like heat sinks and PCBs together. So knowing that you can go a little thicker and still have a thermal resistance that's acceptable is going to be really helpful. Something else, some of the material thicknesses selected, you'll see have a red circle around them. So notice even though that we are getting to a certain thermal resistance, at a certain point the compression pressure is okay, but at lower compression the resistance climbs. So it climbs well above what we consider the maximum. So we don't normally suggest using these because if you are on the lower side of the compression due to tolerance stack-ups, there's a possibility that you are going to have a thermal resistance that's higher than what you've calculated. So going through this exercise, if I were to actually go through the selection process based on the requirements we had previously, basically something like a 2 millimeter material or GAE materials would be a good choice. You could see that basically for what we call 200 GAE, the thermal resistance is below for varying pressures from very low pressure at 14.5 psi to higher pressures. We can also go with thinner materials as well, or even a thicker material if we have very good control of those tolerances. Again, not really suggested if you think that you don't have very good control or you think you might be under-compressing. But generally speaking, something like a 2 millimeter GAE would be pretty good. So would our GDs and GR14As. So all the lower performing materials you see on here would certainly work. Something like our GR25A, as you start getting into some of our really high performing materials like our GR80A, RXRM, obviously you'd have a very low temperature gradient. You'd be able to run the component a little bit higher, but the question is, do you have to? And keep in mind, with these higher performance materials do come quite a bit of cost. So being able to select a material that's cost effective is going to be very helpful early on in the selection process. So in the example we just went over, there are certain assumptions that we are making about the thermal solution, specifically the gap filler. But when you're using them in a real-world application, there are certain factors that will impact the actual temperature gradient, or specifically what you calculate versus actually what you get in real world. So things like heat flux, or specifically the assumption that the heat flux is even over the entire surface of the component, is a big factor. Again, if you're assuming you're getting 4 watts over an inch squared, but the heat flux is much smaller, what you essentially end up is with a hot spot. So in turn, what you're going to have is a higher junction temperature. Also, the assumption that all the heat flow is actually going through the gap filler and through the heat sink out to ambient. Obviously, there's other heat paths that'll actually allow some heat to flow out. This is actually a good thing because it actually helps keep that junction temperature down. Also, the impact of compression on thermal resistance, and we talked about that a little bit previously. Basically, the more you compress these materials, the better thermal resistance you're going to get. Part of that is an improvement in contact resistance, but also keep in mind, you're actually, by compressing it more, you're actually reducing that gap and less of a medium for the heat to transfer through, meaning you're going to get a better thermal resistance. So one of the assumptions we made was that the heat flux is even over the entire surface area of the component, and you have the same heat flux as you go through the gap filler and then down up through the heat sink base. So in our previous example, we calculated the max thermal resistance of the gap filler based on a 1 inch squared, but in reality, the area may be a fraction of that. So in our analysis, we treated the component as one heat source, but actually the die in the package is the heat source, and it is typically much smaller than the actual package itself. What this means is you end up with a hot spot and a lot more power per area than we first thought. So it's difficult to say exactly what that ratio of dye to package is. Never seen it before on a data sheet, but it's a good idea, or at least to be mindful of the fact that all that heat is not going to be traveling through that entire surface area at the top of that package. So it's a good idea to add some margin to your max R theta to accommodate, or calculate it based on maybe half the surface area. If you're working with a bare die or something where the heat source is actually exposed, you won't have to deal with this issue. But if you are dealing with a package, you are going to have to take into consideration that that whole surface area may not be the actual heat flux. So another factor to consider is that not all the heat is going to actually go through the gap filler material up to the heat sink. Keep in mind the package is soldered to a PCB. Metal leads and ground planes, as well as other PCB traces, make very good thermal vias and help dissipate some of the heat. Of course, it's a plus because any heat that's transferred away from the die is a good thing. You're basically going to help reduce your thermal resistance down a little bit. But it's good to be mindful of it. If you're right at the margins, keep in mind that there are other ways to pull the heat out through the traces. So understanding that the very tight heat flux that you have on the package can sometimes be compensated by the fact that you've got other heat transfer mediums, specifically things like the leads and the PCB. And again, another big factor there is that affects thermal resistance is compression. And we touched on it a couple of times before, but it's always worth mentioning again. Creating more compression was definitely going to reduce your thermal resistance, but if there's a possibility the gap will be larger due to tolerances, always check the thermal resistance for that compression. So a good thing is you follow that exercise we did previously where we ensured that the thermal resistance is below max for a wide range of compression. You shouldn't have this issue. Besides just basically doing a basic thermal resistance analysis using a resistive network, there are a lot of tools out there that will really help you understand your overall thermal solution. Probably the most common, obviously, are things like CAD software simulations. I think they're probably one of the best resources you can have. Unfortunately, they can be fairly costly, a little more expensive, but it allows you to have a detailed understanding of the heat flow, temperatures, and temperature gradients, and they can be costly, and training is key as with any software. Some software that I've seen, they do specialize in electronic assemblies. Otherwise, you actually have to physically create the component and some of the attributes to the components. That can be very time-consuming. But there are software out there where they have a pretty nice library. You can basically import the component and set different variables for there. If you can imagine trying to actually build a QFP package or even a TO220 can be very time-consuming. So certain simulation packages that are actually tailored for electronic assemblies are always a great thing to have. Another thing you could have are thermocouple loggers and data loggers. Very useful, kind of a fundamental tool for anybody working in any type of thermal. Many of these loggers have multiple channels, so you can monitor packages and PCBs and heat sinks, and you can even measure, basically create a heat map and create temperature gradients and figure out what's going on. They could also help you out with understanding some of the transient responses. So very useful tool. It's also very useful for basically verifying what you're getting on the CAD or simulation side. Again, you could simulate anything. If you're not seeing it in the real world, then something definitely went wrong. So this resource specific is a very good tool to kind of verify what numbers you're getting in your simulation. Thermal cameras, of course, also very helpful tool, similar to sort of a thermocouple. Basically, you're able to monitor different temperatures. Offers a little more flexibility than a thermocouple. Instead of looking at discrete points, you can actually visually look at the entire layout. It can be a little bit costly compared to something like a thermocouple logger. Typically, what we found is things like the data acquisition on the cameras can vary from one manufacturer, one model to the other. Obviously, very good also for verifying your simulation as well. Also, we talked about how the die, previously how the die is usually much smaller than the package and creates a hot spot. Thermal imaging cameras are actually pretty good at figuring out where those hot spots are. So you can actually kind of accommodate your actual heat surface area based on what you're seeing on that camera. Of course, online resources and publications are great resources as well. There are lots of studies and white papers out there by semiconductor manufacturers. They go into detail about IC packages. Same applies for heat sink manufacturers. Very good resources there. They typically have a lot of white paper, a lot of research. Even though sometimes it's very specific to their product, it is very useful. So that about wraps up our webinar. So just a quick summary. We talked briefly about Fourier's law of heat conduction. Fourier's law of heat tells us how heat flows through a given medium based on a temperature gradient of a temperature field. But we can simplify this down to one dimension and solve for heat flow, temperature gradient, of course, for conductivity. We discussed resistive networks and how to create one, and how to use it to solve for thermal resistance requirements based on your power and anticipated temperature gradient. And this is the type of analysis you can do with a pencil and pad. It's pretty quick to do. It's also helpful to help you visualize the overall thermal solution that you're working on. So one of the things we also touched on is basically data sheets and how to determine material thickness. So one of the great things about the analysis that we did previously is that you can basically come up with a max thermal resistance and then actually go through data sheets and go ahead and pick out what thermal resistance values would be acceptable, and in line what materials would be best suited for it and the material thickness. Okay, we also talked about heat flux, basically how things can vary from your overall analysis to the actual real-world scenario. So heat flux, again, it may vary due to the heat source. So if you are working with a package lid, keep in mind that that whole package is not going to be the entire, you're not going to get even heat flux through that whole package. You are very likely going to get a hot spot. So keep that in mind as you start doing calculations. Again, another cause for variability is going to be the heat path that you're assuming. Keep in mind that there is going to be some heat that's going to transfer from the leads and to the PCB, which actually will help keep some of that temperature down. And we're briefly some of the tools that are available as you start working on different thermal solutions. Of course, computer-aided type of simulations are always great. They can be a little expensive, actually very expensive in some cases, but if you get your folks trained up for that, it's an unbelievable tool. It really gives you a lot of information on the thermal solution. It allows you to play with a lot of variables without having to actually create something in the real world. So really great tools to have. Other things that are more real world, things like thermocouple data loggers, excellent tools to have available. You can just put thermocouples in different places, and not only can you get steady state, but you can also get transient responses if you're interested in something like that. So very basic tool to have whenever you're working with anything thermal, really. Thermal imaging cameras like thermal data loggers allow you to really confirm what your CAD or simulation software is telling you. So also a very, very good tool to have. And of course, one of the best tools you have out there is just online educational resources. With the internet, there's so many places that have got all kinds of resources, not only the vendors that you're working with, but universities and even magazines like Electronic Cooling itself is a great resource. Lots of stuff on there that will really help you kind of learn as you go along and find all the little mistakes that could happen as you go along the way. So lots of tools out there. It's just a matter of keeping your eye out there. Of course, if you have any questions on thermal interface material specifically, you could always contact us. We'd be more than happy to help everyone out.
Thank you, Christian. Audience, if you have any questions you haven't already submitted, now's your chance to enter them into the Q&A panel.
Okay, audience, one last time. If you have any questions you haven't already submitted, now please enter them into the Q&A panel. We do have a number of questions that have come up, so let's get right into it. First question from the audience, is there a specific type of heat sink that is used with thermal gap filters?
No, actually there isn't. You don't really need a specific heat sink. Basically, the thermal interface materials accommodate basically any flat surface. A lot of times we're interfacing housing or a cold plate, for example. So there's no specific heat sink required.
Mm-hmm. Speaking of cold plates, one of our listeners asks, I am using a cold plate. Can I consider its temperature as ambient in my analysis?
Yeah, you can. Basically, as long as the cold plate itself doesn't change temperature based on the heat flux, then you should be okay. And the idea of using a cold plate, obviously, is to maintain a certain constant temperature. And any good design would have a cold plate that can take on that type of load. So yeah, you definitely, if you're doing a resistive network analysis, you can certainly consider the cold plate temperature as sort of your ambient temperature, and then build your resistive network from there.
Mm-hmm. Listener Ivan asks, how do we calculate thermal resistance when we are using heat spreader with thermal interface material?
How do you count thermal resistance when you're using a heat spreader? That's a good question. Yeah, that's a good one. I really wouldn't be able to tell you off the top of my head how would you take that into consideration. The thermal, you could still treat it as a bulk resistance. In other words, if you take into consideration how much is spreading the heat, you should be able to come up with a z-axis thermal resistance. But off the top of my head, I wouldn't be able to tell you. We do work with heat spreaders, but a lot of times that's a kind of a complementary product. The heat spreader suppliers should be able to provide that information in the data sheet for you. They should give it to you as a thermal resistance, just as they would a TIM. The heat spreading capability does add a little bit of a wrinkle to that calculation, but they should be able to provide that for you.
One of our listeners wants to know, what is the mechanism for reducing the thermal resistance as pressure increases?
Well, as pressure increases, you're going to see a decrease in thermal resistance. That's just the nature of the material. And that happens for two reasons. At the low end of the pressure spectrum, you're just going to improve basically the contact resistance. So there's a contact resistance on the hot side and the cold side from the thermal interface. So, but it doesn't take a lot of pressure to overcome that contact resistance. After that, as you increase pressure, what you're actually doing is you're thinning the material out. So there's just less of that material to go through, and in turn, you're going to lower the thermal resistance. But they'll go hand in hand. The more pressure you put on there, the more the material is going to deform, and the lower the thermal resistance is going to be.
Another listener wants to know what minimum thicknesses can we get with gap fillers?
That's a good question, and it comes up quite often, especially when you are dealing with a thin nominal gap that has a fairly high tolerance, fairly wide tolerance. Typically, our materials, products we consider gap filler materials, to get them to much lower than, let's say, like a 200 micron gap is fairly difficult. The reason gap fillers are designed to be thick and stable, mechanically stable. So the fillers are a little bit larger than you would find in something like a thermal grease. That being said, once you get down to these really thin bond lines, it's really the particle sizes or a stack up of the particle sizes that really restrict how thin you can go. Basic rule of thumb, usually with a gap filler material, usually a 200 micron gap is probably as low as you can go. You might be able to go a little lower if you can tolerate a little bit more pressure, but we wouldn't be able to go down to really, really thin bond lines that you would with like a thermal grease, which is really designed to just be a pure thermal interface material.
Another listener wants to know, what are the typical materials that could be used for next generation TIMs for high heat flux applications?
You know, we actually have materials that have fairly low thermal resistance, relatively low thermal resistance when you consider the gap. So we do have materials currently right now. We have something called XM and GR80A, which are typically used for higher heat flux applications. We get thermal resistances depending on how much pressure, but typically about 0.07 degrees C squared per watt. And again, we could improve that a little bit by applying more pressure. So we do have materials currently that will satisfy some of the higher heat flux applications. But it's all relative. I mean, high heat flux for one customer may not be the same for the other. But we do usually with applications that are 100 plus watts per square inch using XM and GR80A.
Another question is, how does pressure affect the thermal resistance of the thermal gap filler?
Similar to the previous question we got on pressure, any increased pressure is really going to improve the material performance. Again, at the low end of the spectrum when it comes to pressure, let's say you're going from 0 to like 5 or 10 psi, you're going to see an improvement in contact resistance. When you go beyond that, you actually start deforming the material, and what starts to happen, the material basically sort of ejects itself from that heat path. So you end up with a thinner material. So thinner material basically means just less mass the heat's going through. So in general, you're just going to end up with a better thermal resistance the more pressure you put on the gap filler.
We have another question on the thickness that you've already answered, so I will skip that. And the question is, when you reference these materials are going to be in service for a long time, define that. How long is that to you?
Yeah, that's a good question. And it's all relative. A lot of our products span from products that are going in for a couple of years, certain consumer products that don't have a long life, but we also work with products that are on, a decade plus. So it's all relative. Unfortunately, we don't have a finite life for these products. We've made attempts to extrapolate life of the products, and I've seen numbers as high as 15 years at max operating temperature, but we really don't have a finite life for this product. It's really more anecdotal evidence. But we are in applications that are type like utility type applications where these devices or systems are out in the field for a decade plus.
Mm-hmm. Our final question is there a thumb rule to calculate the XY thermal resistance of a gap filler?
For X and Y, unfortunately, we don't. As I mentioned in the presentation, these materials are designed for kind of a Z-axis heat transfer. The idea is that this is an isotropic material, but of course it's not homogeneous, so you do have thermal fillers in there, and they tend to conduct in the direction of compression. The idea is that there probably is some difference in conductivity in the X and Y, but because it's not used as a heat spreader, we've never quantified that exact performance. So unfortunately, we wouldn't be able to answer that question for you.
Uh-huh. That's all we have time for today. Thanks again, Christian, for sharing all of that great information with us. All of the questions submitted will be posted on our website with answers, so if we didn't get to your question, you'll be able to find it there. You'll also receive an email with a link to the on-demand version of this presentation in about 24 hours. That wraps things up for today. Thermo Live 2018 will continue tomorrow, beginning at 10 a.m. Eastern Time. We hope you're with us. And until then, I'm Murray Slovic with Electronics Cooling. Thank you for your participation in Thermo Live 2018.